The concept of parallel universes, once a staple of science fiction, has increasingly become a subject of serious scientific inquiry. This idea proposes the existence of multiple universes that coexist alongside our own, each following its own set of physical laws and constants. The roots of this concept can be traced back to the early 20th century, with the advent of quantum mechanics. Pioneering scientists like Hugh Everett III proposed the many worlds interpretation of quantum mechanics in the 1950s, suggesting that every quantum event spawns new, distinct universes for each possible outcome. The evolution of the parallel universe theory has been profoundly influenced by developments in physics, particularly in theories of quantum mechanics and cosmology. As our understanding of the cosmos expanded, so too did the theoretical groundwork for parallel universes. This concept challenges our traditional notions of reality and opens up vast possibilities for understanding the nature of existence. It's a journey from the fringes of speculative thought to a legitimate scientific hypothesis, driven by the relentless pursuit of knowledge about the fundamental nature of reality. The possibility of parallel universes emerges from the intertwining of two major theories in physics: quantum mechanics and general relativity. Quantum mechanics, the cornerstone of modern physics, describes the behavior of particles at the smallest scales. It introduces the principles of superposition, where particles exist in multiple states simultaneously until observed. This led to the many worlds interpretation, proposing that all possible outcomes of quantum measurements are realized in some set of parallel universes. General relativity, Einstein's theory of gravity, describes the large-scale structure of space-time. It revolutionized our understanding of the universe, showing that massive objects curve space-time, affecting the motion of objects and the flow of time. The theory suggests that the cosmos could take various shapes and might be much larger than observable, possibly containing other distinct regions or universes with varying physical properties. The combination of these theories opens a door to a cosmos far more complex than previously imagined. Quantum mechanics implies a multiverse where every possibility exists in some universe, while general relativity allows for the vastness and variability of space-time, potentially housing these parallel universes. These ideas challenge our understanding of reality, suggesting that the universe we observe might just be one of an immense, perhaps infinite number of parallel universes, each following its own set of physical laws. This intersection of quantum physics and general relativity forms the theoretical foundation for the concept of parallel universes, pushing the boundaries of our understanding of the fundamental nature of existence. The nature of time's arrow, the unidirectional flow of time from past to future, is a fundamental aspect of our universe that has intrigued scientists for centuries. Traditionally, the direction of time has been attributed to the laws of thermodynamics, specifically entropy, which describes the degree of disorder within a system. According to this view, time moves forward because the universe began in a highly ordered state and has been moving towards increasing disorder. However, recent theoretical work challenges this view. Julian Barbour, a physicist from the University of Oxford, along with colleagues Tim Kozlowski and Flavio Mercati, proposed a groundbreaking hypothesis suggesting that gravity, not thermodynamics, dictates the direction of time's arrow. Their work, published in Physical Review Letters, argues that the universe doesn't require a special low-entropy initial state to define an arrow of time. Instead, time's progression could simply be an inevitable result of gravitational forces. Barbour's model examines a simplified universe of just 1,000 particles, using computer simulations to observe their behavior under Newtonian gravity. Remarkably, regardless of the initial state of the system, the particles eventually formed low-complexity, tightly packed states due to gravity alone. This observation suggests that gravity could inherently set time's direction without the need for low-entropy starting conditions. Most intriguingly, Barbour's model predicts that after reaching these condensed states, the system expands in two opposite directions, each with its own time arrow moving in a different direction. This bifurcation could imply the existence of two universes, emerging from the same point but evolving separately with time flowing oppositely in each. Such a model presents a radical rethinking of time and its relation to the cosmos, potentially offering a novel perspective of the nature of parallel universes. This theory significantly contributes to our understanding of the universe, presenting a new angle on the origin and direction of time. While it aligns with known laws of physics, it diverges from the traditional entropy-based explanation, suggesting that the phenomena of time and gravity are more deeply intertwined than previously thought. The implications for the concept of parallel universes are profound, opening new avenues for exploring the fundamental nature of reality. The Many Interacting Worlds (MIW) theory, a novel interpretation of quantum mechanics, challenges conventional quantum science by suggesting that parallel worlds not only exist, but also interact with our world. Unlike the traditional Copenhagen interpretation, which posits that particles exist in a state of probability until measured, the MIW theory, as reported by Science Daily, proposes that countless parallel universes coexist with ours and that their interaction could explain quantum phenomena. In this hypothesis, each parallel universe has its own distinct timeline and state of reality, and these universes influence one another. This influence, hypothesized to be a subtle force, could account for the bizarre quantum effects that seem to defy classical physics, such as particles being in multiple places at once or affecting each other instantaneously over vast distances, quantum entanglement. The implications of the MIW theory are profound. If parallel universes interact, it could revolutionize our understanding of the universe and offer new explanations for quantum mysteries. This theory suggests that what we perceive as quantum phenomena might be the result of tangible interactions with other nearly identical worlds. It stretches the boundaries of our understanding of reality, hinting at a complex, interconnected multiverse where the boundaries between worlds are not as rigid as once thought. This idea, while still speculative and requiring more scientific validation, offers a fresh perspective on the foundations of quantum mechanics and the potential reality of parallel worlds. The quest to understand and validate the existence of parallel universes faces significant challenges due to the constraints of current scientific capabilities. As discussed in Big Think, a major hurdle is the inherent limitation in testing and observing phenomena that may occur in these parallel universes. The fundamental issue lies in our confinement within our own universe, bound by its physical laws and constants. This limitation makes it nearly impossible to directly detect or interact with other universes if they exist. Our current understanding of physics, based on the standard model of particle physics, effectively accounts for known forces, except gravity, and particles within our universe. This model has been remarkably successful in explaining a wide range of phenomena. However, it does not provide a mechanism for interactions with other universes. All known experiments and observations conform to the idea that our universe is self-contained without requiring external universes for explanation. Additionally, our scientific instruments and methods are designed based on the laws and properties of our universe. As such, they may not be sensitive or applicable to phenomena that could potentially signify the existence of parallel universes. Theoretical models like the Many Interacting Worlds theory propose fascinating possibilities, but translating these theories into testable experiments remains a significant challenge. In summary, while the concept of parallel universes is a tantalizing and intellectually stimulating one, the current state of science faces considerable limitations in empirically testing or observing these alternate realms. This presents a frontier in physics that is as exciting as it is elusive, requiring innovative approaches and perhaps new laws of physics to bridge the gap between theory and empirical evidence. The Antarctic Impulsive Transient Antenna (ANITA) experiment represents a significant stride in astrophysics, particularly in the search for evidence of parallel universes. Deployed in Antarctica, ANITA is designed to detect ultra-high energy cosmic neutrinos by using a giant balloon to hoist an array of antennas high above the ice. These neutrinos are fundamental particles that can travel through most matter almost undisturbed, making them ideal messengers for probing cosmic phenomena. ANITA's findings have stirred considerable interest due to their unusual nature. The experiment detected radio waves emanating from the Antarctic ice, which are interpreted as remnants of high-energy neutrinos colliding with the ice. Intriguingly, some of these signals appeared to be coming from a destination that suggested the neutrinos were traveling upward from the Earth, which contradicts the expected behavior of such particles according to standard models of physics. This anomalous observation led to speculation about its possible implications for the existence of parallel universes. One hypothesis is that these neutrinos could be particles from a parallel universe that operates under a different set of physical laws, possibly where time runs backward. This concept aligns with some interpretations of the many worlds theory in quantum mechanics. However, it's crucial to note that these findings are still subject to significant scientific scrutiny. While the anomalies detected by ANITA are exciting and potentially groundbreaking, further investigation and corroborative evidence are needed to draw definitive conclusions about their nature and the existence of parallel universes. The ANITA experiment highlights the cutting edge of astrophysical research and the ongoing quest to understand the deepest mysteries of the cosmos.